Trapezium rule. Trapezium rule is just basically a way of you finding an approximation for an area under a curve. It's not perfect, but it is pretty good way of doing it to find an approximation. I'm just going to look at a wee sketch here and see what we're talking about. So if you imagine you've got a curve like this, and you want to find an approximation for the area under this curve, what you could do is split it into trapeziums. So if I split it into two trapeziums, for example, if I wanted to find the area between A and B, you could split it into two trapeziums, and if I do a straight line between those, you can see I have two trapeziums there, and that's a pretty good approximation for the area underneath that curve. If I went back on that and I split it into four trapeziums, you can see that they more closely follow the curve, so that's a more accurate way of seeing it. And if I went back again and split that into maybe 6 pieces, so there's 6 trapeziums. If I link those up, you can see then that is an even more accurate area under the approximation to the area under the curve. So basically, the more trapeziums you split the curve into, the more accurate it is going to be, the more closer it's going to be to the actual area of the curve. Okay, we're going to look now at how we actually do this, how we use this trapezium rule. This example says, find an approximation to the area bounded by y is equal to 1 over 1 plus x cubed at the axes and what x equals 1. So what we're going to do is we're going to do a little sketch of this thing. First of all, this curve. So I'm just going to pick a few values. So I'll do my x values and corresponding y values. Doesn't tell us to use a trapezium rule or anything here. This is just introducing the trapezium rule, or the fact that a curve can be similar to a trapezium. So when x equals 0, y is going to be 1 over 1 plus 0. So it's just be 1 over 1, which is 1. And then use your calculator, please. I'm going to pick x equals 0.3, x equals 0.6, and I'll use x equals 1. You could use any values in between. But when you put 0.3 into that, you'll have 1 over 1 plus 0.3 cubed, and that gives you 0.97. Put 0.6 into it, 1 over 1 plus 0.6 cubed will give you 0.82. Put 1 into it, you're going to have 1 over 1 plus 1, 1 plus 1 is 2, 1 over 2 is just 2, which is 0.5. Okay, so if you sketch, this is just a sketch. And if you do this sketch here, the curve looks very roughly like this. It starts up at 1, and then it curves down like this, and that is 0.5. Okay, I need to find the area between 0 and 1. Now, what you would do, if you're doing this properly and finding the actual area, you'd be doing the integral of 1 over 1 plus x cubed dx between 0 and 1. That's what the area would be. Right? I don't know how to do that. So what we're going to do is, what the question's asked to do is an approximation. So we can see here, if we drew a line, straight line from here to here, I haven't used a ruler, but you would use a ruler if you were doing that. That really is what the area we're going to do. So this trapezium I've drawn in black is a fairly rough approximation for the area of that curve. So I'm just going to say, estimating the area as a single, estimating the area as a single trapezium. So you're going to say your area is equal to, and if you remember way back to GCSE level mathematics, the area of a trapezium is a plus b, half of a plus b times h. So it's a half times the parallel sides times the perpendicular distance between them. And my parallel sides are, so there's a parallel side, which is 1. There's another parallel side, which is 0.5. So my area is going to be a half, my area is going to be a half times 1 plus 0.5, and then my perpendicular distance between them would be this distance here, which is also going to be 1. So my h is 1. So that's really a half of 1 plus 0.5, which is 1.5 times 1. So a half times 1.5, which is just going to be 0.75, and I'll say units squared. Okay, so as I mentioned earlier on, for more accurate results, the area can be approximated by dividing it into a number of trapezium and adding their areas. So the formula for the trapezium rule we're going to look at here. So the formula for a trapezium rule is as follows. You've got your first thing I like to do is draw the shape out. So draw out what you've got. And if I'm doing a sketch of this, no matter what the curve is, I would always sort of draw this sort of shape anyway. It just makes it an awful lot easier. And then your normally area, if you're finding the area between A and B, you'll have it split out into a certain number of strips. Now you've got the first height then. This is the height when x is equal to a, or it is a y value when x is equal to a. That's why we call it y1. The next one, whatever this x value is, this would be y2. Whatever this x value is, this is y1, then y2, then y3, y4, all the way up to your last one is yn. So the one before that would be yn minus 1. And okay, so the first strip, the area of the first strip, if you looked at the area of the first strip, area of your first strip is a half times y0 plus y1. That's where y0 and y1 are the parallel sides, and h is a perpendicular distance between them, so h is the height. So that's what you have. Your area of your second strip is a half times y1 plus y2 times h, and so on. So if we continue that on, and h, by the way, can be calculated by b minus a, so the distance between a and b, and then divided by n, where n is your number of strips, and that's very, very important. Okay, so if we scoot on down to the next wee bit, so the total area is going to be equal to, if you imagine this one we've just done, total area is h over 2 times y0 plus y1 plus h over 2 times y1 plus y2 plus h over 2 times y2 plus y3, h over 2 plus y3 times y4, all the way up to h over 2 times yn minus 1 plus yn. Okay, so very importantly, folks, if you tidy this all up, what you have is h over 2 times y0, y1 plus another y1 plus another y plus y2 plus another y2 plus y3. There'd be another y3 in here. All the way along, you'd have the term before this would be yn minus 1 plus another yn minus 1 plus yn. So very importantly, all of them have been added twice, like y1 has been added twice, y2 has been added twice, y3 has been added twice, etc. All of them except y0 and yn. So your whole formula can be abbreviated to h over 2 y0 plus yn. That was your two n values, or else you could say your first and your last, and then 2 times the others, or else you could say the rest. So the y1, the y2, the y3, all the way up to yn minus 1, they're all getting added twice, so that's why there's a 2 in front of it. So how you want to remember this, and you will not remember this formula very well, but if you remember it in words, it will help you an awful lot. So this formula here, remember it as area is equal to a half times h times the first plus the last, and then times 2 times the rest. And that is because y0 and yn appear only once, where every other term appears twice. Okay, we're going to go back to doing the first example we did, except we're going to do it properly. So we're going to do it now with using a certain number of strips, which they will give you in the examination. So it says, now consider y is equal to 1 over 1 plus x cubed between x equals 0 and x equals 1, and split it into 5 strips. So 5 strips, if you imagine 5 strips, 1, 2, 3, 4, 5. There's 5 strips. 1, 2, 3, 4, 5. Yep. And that means there's 6 ordinates. So where that comes from, an ordinate is just an endpoint. So you can see those wee dots I've just put on. There's 6 of them, so there's 6 endpoints. So that's really what we mean. So the number of ordinates, the number of endpoints, is always one more than the number of strips. Okay, so you can see I've set up my table here. I've got my x values. I've got my x values here, and they're in a column. And then I'm going to have my first and my last, and then I'm going to have my rest. And this is our formula. So this is how we calculate the corresponding y values. We're going to put x values into this to see what we get. So let's just do a sketch before we get started. I'm going to do the same sketch that I always do. So my sketch is not accurate at all. It is just the same shape that I always do when I'm doing this. So I just do a random wee curve, A and B. That's my endpoints. And what are my? If you know your A and B, put them in. And we do know our A and B here. So our A and B are 0 and 1. And then how we'd work this out then? The distance between 0 and 1 is just 1. We have 5 strips, so 1 divided by 5 is 0.2. So every one of these is going to be 0.2. So it's going to be 0.4, 0.6, and then 0.8. So you can see here h, and very importantly then, that you can see they've worked that out up here. H is equal to 1 minus 0 divided by 5 is 0.2. But let's write that in again. H is equal to 0.2. So that's the width of your strip, or the height of the strip, we could say. So if you can imagine, if you put those wee trapeziums in, you can see it's a very good approximation to the area on this curve. Okay, we've got to find then the heights of all these things. So we're looking to find these heights. So to find this height, this is one of our first and our last. So you're putting x equals 0 into this equation. So when we go through and do that, put x equals 0 into that, that's 1. The next one we're going to find is this height, but this goes in this column, remember, because this is in the rest. So when x equals 0.2, put that in. And if the calculator lets you, if it gives you a fractional answer, leave that as a fractional answer because it's perfect. So, and my calculator did, it was 125 over 126. My next one, so this is putting in 0.4. When I put in 0.4, I got 125 over 133. When I put in 0.6, I got 125 over 152. When I put in 0.8, I got 125 over 125 over 189. I read the same one twice, 189. And then when I put in 1, and remember 0.1 goes into 1 goes into this column because it's one of my end ones. When you put in 1, you get 0.5. Now the easy way to do this is just to total up these things. So the total goes in the bottom in here. So I'm going to total this up and then total up this column. When I total up this column, I get 1.5. When I total up this column, didn't get a particularly nice number. It didn't leave it as a fraction, so it's 3.41566. And then we're ready to do our put this into our formula. So we'll write down the formula again. Formula is the area is approximately equal to a half h, or h over 2, and then times, and then the way we set it in our notes here was first plus the last plus 2 times the rest, and then we're just going to fill this in. So h, remember, was 0.2, so it's 0.2 over 2. My first plus the last worked out as 1.5, and 2 times the rest was 3.41566, and then you can put that into your calculator in one go and see what you get. So it was 0.833132, which was equal to then 0.833, and that's the 3 sig figs. Our last example says, find an approximation to the area bounded by the axes, x equals 2 and the curve, using a trapezium rule with 5 intervals. So it is the axes, so both axes end, so that means you're going from x equals 0, and then x equals 2. So the total width is equal to 2. Again, there's 5 strips, so h is equal to 2 divided by 5, which works out to be 0.4. So I'm going to do out my table first with my x values, and then I'll do my wee sketch. So my table is like this. I'm going to have, and I'll call it the same way we've set it in earlier on, first plus the last. And then this is your rest. So my first value is x equals 0, and then we're going up on 0.4, so 0.4, 0.8, 1.2, 1.6, and our last one, which is 2. And then we will leave a wee space in to be able to do the totals at the end. So let's just do a wee sketch, just to keep us right what we've got. And this is just a sketch. So we're starting, there's your axes, and you're starting at 0. We'll just do it from the axes, the vertical axes. Don't know or care what this looks like, but it's 0 to 2, and then we're going up. I think I left myself enough space, just about. Use your imagination there. 0.4, 0.8, 1.2, 1.6, and 2. So there you can see what we've got, and then your distance between them, we'll say that's your h, and h is equal to 0.4. So it's just a wee sketch to keep me right. So what I'm going to do then is I'm going to find these heights. Don't be worrying about the sketch, it's just sketch. Didn't put any thought into the sketch at all, just to give me some sort of visual idea of what's going on. So when you put in 0, you get the first height. So 1 over 1 plus 0 is just going to be 1. And that goes in my ends bit. Now I'm on to this one. This is when x equals 0.4, which is in the rest column, as we'll go. When I put it in, I got 25 over 29. When I put in 0.8, I got 25 over 41. So they're perfect. And that's 25 over 61 for the next one. 25 over 89. And then I've done all the ones that are the others or the rest. And then I'm on to my last end one. So this is putting x equals 2 into it. Put in x equals 2, I will get 1 over 5. So when you add the first column up there, the first and the last, you'll get 1 and 1/5, which is 1.2. It's a nice decimal. I'll just put it in as a decimal. Sorry, the next one then, you add them up, you'll get 2.16256. And then my formula, remember my formula is the area is approximately equal to h over 2. We know we're h. And then the first plus the last plus 2 times the rest. And then we just fire in whatever we know. So our h is 0.4. So 0.4 divided by 2. The first plus the last is 1.2. And 2 times the rest, which is 2.16256. And then if you do that out, that becomes 1.105024, which is approximately equal to 1.11 to 3 sig figs. Okay, that is the end of our trapezium rule. So we now know how to find an approximation to the area under a curve by splitting it into trapeziums with equal widths.